Imagine a future where quantum computers can tackle problems that are currently beyond the reach of even the most powerful supercomputers. These revolutionary machines hold the potential to transform fields such as cryptography, material science, and drug discovery. However, there's a significant hurdle. Quantum computers are incredibly delicate. The quantum bits, or qubits, that are essential for storing and processing information are easily disturbed by minor influences. Factors like heat, light, or magnetic interference can disrupt their fragile quantum states, leading to rapid accumulation of errors. One of the most exciting avenues being explored to overcome this challenge is topological quantum computing. This innovative approach safeguards information by encoding it within the geometric characteristics of unique particles known as anyons. Unlike standard particles, anyons can only exist in specific two-dimensional environments. Theoretical research indicates that they are much more resistant to noise compared to traditional qubits, making them promising candidates for constructing a robust quantum computer. Aaron Lauda, a professor specializing in mathematics, physics, and astronomy at the University of Southern California, elaborated on the appeal of a particular type of these particles. Ising anyons are among the top contenders for developing such a computer. They are currently under intense investigation in condensed matter laboratories due to their potential realization in exotic systems like the fractional quantum Hall state and topological superconductors. However, Ising anyons come with their own limitations. They store quantum information through a technique known as braiding, which involves physically moving them around each other. This movement alters the overall quantum state in a predictable manner, enabling quantum logic operations. Yet there's a significant limitation. Braiding Ising anyons can only execute a limited range of logic operations known as Clifford gates. This means they cannot independently manage every conceivable quantum computation. To address this limitation, physicists have been investigating alternative methods, such as incorporating operations that are not protected by topology or utilizing short-range interactions between anyons. While these strategies can enhance computational capabilities, they often necessitate complex error correction processes, which can detract from the inherent stability that makes anyons so appealing in the first place. In a groundbreaking development, a research team led by USC has discovered a way to make Ising anyons universally applicable for quantum computation, using only braiding. Their findings, published in Nature Communications, introduce a new particle type that fills a crucial gap in the Ising anyon toolkit. They have named this particle the Neglecton, a term chosen because it was previously overlooked in earlier mathematical analyses. This novel particle emerges from a broader theoretical framework known as non-semisimple topological quantum field theory, are discarded as mathematically insignificant. However, in the non-semisimple version, these previously discarded objects remain, and one of them is the Neglecton. Lauda remarked, "Those discarded objects turn out to be the missing piece. It's akin to discovering treasure in what everyone else considered mathematical trash." The elegance of this approach lies in its simplicity. Only one Neglecton is required, and it doesn't even need to be in motion. The computation occurs entirely through the braiding of Ising anyons around it. Nonetheless, non-semisimple theories introduce their own set of challenges. They can violate a fundamental principle known as unitarity, which ensures that quantum probabilities always sum to 1. Many researchers would view this as a critical flaw for any quantum computing model. Lauda's team has devised a workaround. They structure their quantum encoding so that any unstable mathematical behavior does not interfere with the computational aspects of the system. Imagine designing a quantum computer in a house with some unstable rooms, Lauda explained. Instead of trying to fix every room, you ensure that all your computing takes place in the structurally sound areas while keeping the problematic spaces off limits. In this configuration, the computational Hilbert space, the mathematical realm where qubits reside, remains perfectly stable. Any issues related to unitarity are isolated in unused sections of the theory. The team's findings build upon decades of research into the fractional quantum Hall effect, a phenomenon observed in ultra-clean two-dimensional electron systems subjected to strong magnetic fields. In specific scenarios, such as the nu equals 5/10 filling fraction, these systems are believed to host non-abelian anyons, including Ising types. The nu equals 5/10 state has been experimentally observed and aligns with the Moore-Reed-Pfaffian wave function predicted by conformal field theory. These systems are particularly appealing for topological quantum computing due to their large quasi-particle gap, which makes it difficult for stray thermal excitations to disrupt computations. Additionally, since anyons carry electric charge, they can be manipulated using electrostatic gates that exhibit very low error rates. The new theoretical framework enhances this by introducing the stationary Neglecton as a computational anchor. If experimentalists can identify a material platform that naturally produces this type of particle, they could achieve universal quantum computing with particles that are already well understood in condensed matter physics. Lauda expressed enthusiasm about this development, stating, "What's especially thrilling is that this research brings us closer to universal quantum computing, using particles we already know how to create. The mathematics provides a clear target." If experimentalists can find a way to realize this additional stationary anyon, it could unlock the full potential of Ising-based systems. Braiding anyons is not merely a theoretical concept, it has practical implications. In reality, it involves moving particles along meticulously designed paths so that their exchanges yield specific quantum gates. The researchers demonstrated that by braiding pairs of sigma anyons, a type within the Ising family, around groups of other anyons, controlled operations can be created that entangle qubits. They also outlined a strategy to minimize leakage into non-computational spaces, which is crucial because if a computation strays into unused areas of the Hilbert space, it can lead to errors. Their method constructs these control gates iteratively, avoiding complex mathematical shortcuts like the Solovay-Kitaev theorem. The physical realizability of this new model may bear similarities to that of Fibonacci anyons, another powerful non-abelian type believed to exist in fractional quantum Hall systems at nu equals 12/5. Fibonacci anyons can achieve universal quantum computation solely through braiding, but their simplest chiral form cannot be realized by a straightforward two-dimensional lattice Hamiltonian. A doubled version can be, and this insight has guided researchers in developing the Levin-Wen model, a lattice framework that supports gapped, topologically ordered states. Lauda's team has been working on non-semi-simple versions of these Levin-Wen models, which continue to produce stable ground states and anyonic excitations, despite having indefinite norms in their mathematical structure. This connection suggests that neglectons might be realized in gapped systems under the right conditions. Looking ahead, certain condensed matter systems, including specific spin chains with modified boundary conditions, could potentially host these new anyon types. These clues provide experimentalists with a starting point for searching for neglectons in the laboratory. Fractional quantum Hall states remain the most promising path forward, especially since researchers already possess the knowledge to create and manipulate Ising anyons in these systems. If the Neglecton can be successfully realized, it would pave the way for constructing a universal topological quantum computer without relying on fragile, non-topological operations. This advancement could represent a monumental leap forward for quantum technology, offering the long-desired combination of universality, scalability, and fault tolerance. And it all began with the decision to not discard what the mathematics deemed useless.